Hello, hi everyone. Welcome to today's CMCC webinar on Oceanic mesoscale in the climate machines. I'm Enrico Scoccimarro. I'm going to be the moderator of the present seminar, and we are going to follow Dorotea Iovino's speech in a few minutes. Let me spend before a couple of slides on what do we do at CMCC. CMCC is a research institute with the aim to investigate and model our climate system and the interaction with the society. The idea is to provide rigorous scientific results to stakeholders for the development of science-driven adaptation and mitigation policies in a changing climate. So the CMCC has different divisions in different locations across Italy. In Lecce we have the headquarters and the computing center. There are 9 divisions at CMCC, ranging from the advanced scientific and computation to the global and regional climate modeling. This is done for both the atmosphere and the ocean, and also for coupled models. And also we have division devoted to the study not only of the physics, but of the impact of climate variability and climate change on agriculture, forest, and economic aspect. So there is also a division on risk assessment and adaptation strategies and sustainable and earth modeling economics. These divisions are all working with the aim to provide scientific results to the community, and all of the divisions are linked by different topics, are the one you can see listed here. And together with the publication of scientific results and technical reports, project reports, we also are involved in communication efforts and in the organization of different events. And for instance, this CMCC webinar is one of the tools we use to distribute the information we are working on at CMCC. And today, in particular, we are going to talk about Oceanic mesoscale and the climate machine. And this is a seminar that will be led by Dr. Dorotea Iovino. Dorotea got her PhD at the University of Bergen in physical oceanography. She then spent a period at l'Oceanic in Paris, at the Laboratory l'Oceanic in Paris, and she expanded her knowledge and experience in oceanography and numerical modeling. She is now at CMCC in Bologna. She is part of the Ocean Modeling and Data Simulation Division. She is currently a scientist here since 2012, I would say, and since 2015, she coordinates the research activity of the Ocean and CEST modeling group of the division. She has been involved in many national and international projects, and since 2017, she is a member of the CLIVAR Northern Ocean Research Panel, and she is the NEMO officer for the CMCC. She also teaches at the PhD program in Science and Management of Climate Change at the University of Ca' Foscari. But let me stop here. I already spent too much time. Dorotea, the floor is yours. Please collect all of the questions you have in the portal, and then at the end we will discuss together with Dorotea, and we'll provide you all of the answers. So, Dorotea, the floor is yours.
So, thank you, Enrico. I'm waiting for sharing the screen. So, here we go. So, thanks, Enrico, for the introduction. The webinar, as you say, is going to focus on the relevance in a numerical modeling exercise of properly resolved ocean dynamics, and in particular the ocean activities that occur on a specific space and time scales. We all agree, or at least we should all agree, that the ocean dominates the global reservoir of water, heat, CO2, and because of that, it plays a central role into the climate machine. So ocean properties and also the ongoing change due to the anthropogenic influences can have huge climatic consequences. To a large extent, ocean circulation control, for example, the biomass or biogeochemical cycle, the ocean acidification, or the uptake of heat, or, for example, what is frequently discussed now, the regional pattern of change in sea level. So the challenge of understanding and predicting climate change represents also a significant challenge for modelers in modeling the ocean circulation and ocean dynamics. I'll show here some example of the benefits of at the ocean modeling, so resolving mesoscale eddies into the ocean component of the system, and also some example on how that can impact other components of the climate machine. So the role of ocean circulation into the climate system is linked to a range of scale interaction mechanisms, each with a different dynamical nature. We can go from the gyre of the circulation that span entire ocean basin to the small scale physical processes that occur at scales that are smaller than 100 kilometers, for example. So these ocean dynamics, they are much smaller than the size of the ocean basin, includes, for example, meanders or eddies, what we can generally call like mesoscale turbulence. Also boundary currents, narrow boundary currents that follow flowing along the continental shelf and over the slope. So they both contribute to a large part of the oceanic transport of heat and fresh water from the low latitudes to the northern parts of the world, to the polar region. So ocean mesoscale eddies can be identified or defined as the weather of the ocean that can be like the equivalent of the storm into the atmosphere. So over the past decades, the combination of satellite remote sensing and also the improvements in ocean modeling has showed the ubiquity of the ocean mesoscale processes, and also have highlighted the role that they have into the climate. But there are still a lot of key questions that are unresolved, and mesoscale processes are still challenging to be represented realistically into the ocean models. So the fine scale eddies and the narrow boundary currents, if you think, for example, of the climate model that we use in the last IPCC assessments, are absolutely not yet adequately represented. So their contribution in climate needs much more investigation and improvements from the modeling part. So our challenge as in oceanography, also in climate science, as modelers, is to improve the simulation and interaction, and the simulation and the understanding of those mechanisms, and the link between the fine scale processes, the large scale variability, and also the interaction between the ocean component and the rest of the air system. So if we agree that the ocean is turbulent, what you see, for example, here into the plot, is the sea level anomaly computed from Aviso datasets, and you see a lot of patchiness. So the unsteady dynamics gives the ocean a rich texture, and all that corresponds to the small scales that I'm talking about. So you see they move zonally or meridionally everywhere into the ocean, and their presence more or less everywhere at any latitude. So mesoscale eddies typically have different properties of their surroundings. So they have they are generally characterized by anomaly in temperature and salinity, for example, with associated flow anomalies also. So that allow them to transport properties like heat, salt, or carbon through the ocean, or, for example, supply nutrients to the coastal region or to the coastal areas. Or, for example, if we think about the Engulus eddies in the south of Africa, they carry water with properties associated with the Indian Ocean far into the South Atlantic, or into the Southern Ocean. If you think about the ACC, eddy actually accounts for the majority of the polar world heat transports across these strong currents. So eddies are responsible for the mixing of water with different processes, and they are also important because they have kinetic energy associated to them. So mesoscale eddy usually account for the peak in the kinetic energy spectrum. At least more than half of the kinetic energy that is available for the ocean circulation is contained in the mesoscale fields, with the rest largely contained in the large scale circulation. So the large scale eddies, so the mesoscale eddies emerge generally for instability of the strong horizontally sheared motion, particularly in the boundary current as the Gulf Stream. That's what you see into the movie here. The movie represents the surface current computed by an eddy ocean model on global scale. It's called Globe 16 that I'm going to introduce later in the next slides. So these eddies often take the form of defined rings. They are easily identified here into the plot. I don't know if you can see the mouse, but I'm trying actually to show some of them. So they are well-identified rings. They can extend also at depth, even though we are looking only the velocity field at surface here. On the order of smaller scale, tens of kilometers, eddies can be also generated by the slumping of horizontal density gradients, so what is generally called baroclinic instabilities. So in both cases, we can say that mesoscale dynamic is anyway strongly coupled and linked with the large scale circulation. But the dominant length scale of these eddies varies a lot greatly with latitude, with the stratification, and also with the ocean depth. So as seen, the ocean circulation is pervaded by mesoscale everywhere at any latitude band. We saw that in the previous movie, but that characteristic change with the location. So their size varies with latitudes and the other factor of the environment, for example, the topography or the nature of the generation. But they typically have the horizontal scale of the order of the first baroclinic Rossby radius of the formation. That is of fundamental importance into the ocean dynamics, since it's kind of the natural scales of the boundary currents at the same front in ocean dynamics. It can scale from 100 kilometers at low latitudes, and it's much smaller, around few kilometers when we move polarwards. But also the scales of the eddies varies with vertically, so they generally are the depth of the pycnocline, but can be much deeper than that, and they can cover time scale that goes from few days up to weeks or months. Here we have an example into the bigger plot of how actually the baroclinic Rossby radius change with latitude. This is old plot that is commonly used, comes from paper by Cherton. And what we see here is that, let's say, the scale of the eddies, it's really large when we stay in the tropical region. So we are about 200 kilometers. But as we move at high latitude in both hemispheres, number gets smaller and smaller. So number actually indicates how in kilometers the size of the eddies, the typical size of the mesoscale fields. So if we stay, for example, into the North Atlantic, just before entering the Nordic seas, we are around only 10 kilometers. If we go up northwards into the Arctic Ocean, for example, what we see from the other plots that also show the Rossby radius computed in this case from temperature and salinity profiles only into the Arctic is the PHC dataset, where you see actually that the scale is even smaller. There are areas of the Arctic Ocean when the Rossby radius it's around 10 or 15 kilometers, but if we stay on the shelf, for example, we need the resolution, or we need to resolve dynamical fields. They are only few kilometers with the scale of only a few kilometers. So the blue-violet is actually below 2 kilometers. So the numerical modeling is, of course, an essential tool to represent and to understand the climate system, and also for the ocean components. So if we can assess, the accuracy or the fidelity of the ocean simulation in a more rigorous way due to the enhancement of the realism in representing also the ocean processes. And that's partially due, or at least for a larger extent, is due to the increase into the grid resolution. So this is fundamental to perform simulation in which much of the ocean variability is explicitly resolved, and the eddy dynamics and also their life cycle is realistically represented. But we also have to take in account that increasing resolution means that the computational cost of the simulation gets higher, and also we have to face the challenge of the high performance computing and or what that means for a modeler. So the crucial question when we plan a new simulation at high resolution, including the ocean component, is actually how the spatial resolution of the new configuration has to be prepared. So which kind of dynamics we want to solve, and what's the cost of doing that? So mesoscale, what we see here from the plots is that mesoscale is adequately described as long as the grid spacing is finer than the first baroclinic Rossby radius. So comparing our resolution to the field of the Rossby radius, we know where the model will describe boundary currents at the fields in a proper way and where the model will not. Oops. So the point is that this kind of choice are not only cannot be only scientifically based. Of course, the modelers wants to push the numerical tools in complexity and resolution as much as possible, but we always have to take in account that we have to balance all the system. So more complex model or higher resolution model or higher number of ensemble member, for example, it's always good for science, but that also means that the computer cost that actually we are asking for is much higher. So the choice that we have to do is take in balance all these kind of different points. So not only aiming for having really long simulation with the most complex hair system model with a lot of members or really long historical runs. So the strategy that we choose here at CMCC into the ocean modeling group is to improve, of course, the ocean by increasing the resolution and also enhancing the complexity of the code by itself. So most climate and also global ocean models have the horizontal space grid spacing that is generally 2 cores. So for example, the last CMCC exercise, typically the resolution was about 1 degree. So that cannot explicitly represent mesoscale eddies. But even the newer climate model, I will show plots later, also for this one, the grid spacing that is typically 1/4 degree now, it's said to be only eddy permitting, but not eddy resolving. Those cannot be called eddy ocean. So in all this model, the important effect of the unresolved eddies needs to be parameterized to have, let's say, proper solution from the ocean point of view. So duration of the model grid spacing to the Rossby radius gives us an indication of whether a model will be locally capable to resolve mesoscale eddies. So the plot that we have here is somehow similar to what we saw before from Shelton. That's a plot coming from a Holberg paper and gives us an indication on the resolution that the model needs to resolve the Rossby radius with only 2 grid points. So keep in mind that generally for resolving the mesoscale dynamics, we need at least 5 grid points, 5 delta x. So the picture should be or could be much more restrictive than one that we have on these plots. But anyway, what we see here, that if we are at 1 degree resolution, so if we look at the light blue colors, we can resolve actually eddies only into the tropical bands. Even if we stay at 1/4 of degree, so the eddy permitting ocean resolution, so we jump between the blue, the darker blue, and the green, we stay only at mid-latitude. So we can resolve mesoscale in the subtropical region, but not northern than that. Typically, we say that the ocean, the ocean is considering eddy resolving if it has at least 1/10 of degree resolution. So if you are about here into the model. So if we stay into the last acid green colors, what we see is that we are kind of on the margin of the subpolar gyre, for example, into the North Atlantic, or we are say northward of the ACC into the Southern Ocean. So also in this case, actually, the 1/10 of degree that's for years has been considered already eddy resolving is actually not. So at CMCC, what we did is to push a bit more the resolution, and we decided to build a global configuration that is at 1/16 of resolution, so where we jump between the yellow and the orange color. So also in this case, based on these plots, we see that we cannot explicitly resolve eddies everywhere into the global ocean. For sure, we miss all the shelf and continental slope area, but at least if you are into the open ocean, the model is actually able to resolve the mesoscale also at the high latitude, so also into the Antarctic Ocean and mainly into the Arctic Ocean. And also I want to mention that CMCC is highly involved at the moment in building the new target global configuration in NEMO that will have like a global really high resolution starting from 3 kilometers at the equator, going up to 1 kilometer into the northern, into the polar region. But let's stick on the 1/16 resolution. We call this configuration the Globe 16. At the moment, at least, is the global configuration based on the NEMO framework having higher resolution everywhere into the ocean. It's based on the release 3.6. And the ocean component is coupled to the Luvanayev CI's model, namely SLIM2 in this case. We built the grids as generally is done for other global NEMO configuration. So it's structured grids with 3 different poles, 2 placed into the northern hemisphere on Siberia and Canada, and 1 place with the South Pole, actually collocated with the South Pole. As I said, the resolution is 1/16 of degree. That means slightly less than 7 kilometers at the equator. And then the resolution, of course, increase with the latitudes. So we end up to have 2 kilometers, slightly 2 kilometers into the Canadian archipelago in the Arctic as the highest resolution that we have. The model has 98 vertical levels. That makes the number of grid points really high. Few details on the bathymetry. There is a combination of different products. We use E2Po2 that doesn't need a lot of smoothing into the deep ocean. We had the JEBCO for the continental shelf and all the coastal area, and we update the bathymetry using the NASA product BEDMAP2 for the Arctic Ocean, including also the high sheets, age, and coastlines. With this configuration, we actually run now a set of different simulations with different lengths. Most of them are hindcast. All of them employ the core back formulation, the one coming from Lars J. Jaeger 2009 publication. But we tested, or we used the configuration with different forcing or atmospheric reanalysis, going for era interim, ECNWF, the operational system, and the last runs that we are performing actually use the last version of the 1.4 of the JERA 55 do reanalysis. Here is an example of the benefits of the enhanced resolution on the one particular property of the ocean. We're looking here at the heat transports into the North Atlantic. So into the upper plot, you see in petawatts the heat transport as function of latitudes. And you have a bunch of different observation, in situ observation. There are the triangles with uncertainties, and then you also have some estimates coming from atmospheric data sets. And the solid line represents two different simulations. The red one is the Globe 16 that I have just presented, while the black one is a similar NEMO configuration coupled with CIs forced with the same atmospheric reanalysis, with a very similar setup, but having lower resolution. So the black line is only eddy permitting simulations. And it's pretty clear if you stay into the North Atlantic that having higher resolution means that actually we are largely increase in all latitudes the amount of heat that moves polarwards by the ocean circulation. The path is also different. For example, there is large impacts on the path of the circulation when we go at latitude of the Labrador Sea. And that's also evident here, where there is not these large decrease into the heat transport if we stay into the Globe 16 simulation. Here you have indication of some observation that comes from different ray and different latitudes. In all cases, Globe 16 compares much better than the Orca 025 to those observations. It's one particular latitude, the 26.5 into the North Atlantic. We have the comparison with the long array by rapids. And here where you see rapid is in blue, while the two configurations are in red and black again. And also in this case, it's pretty visible, it's pretty clear that Globe 16 follow, actually both of them follow the variability of rapids, but Globe 16 is clearly much closer to observation for this 10 years period. We have already mentioned that the kinetic energy associated to eddy, it's kind of the clear, one of the key points or the key contribution of eddies into the ocean. And eddy kinetic energy can be considered like a measure of the intensity of the mesoscale activities. So eddy kinetic energy tends to be the greatest where the mean circulation is the strongest. That means that eddies derive their energy from that's because eddy derives their energy from the mean circulation. So if you look at the upper panel, we have the horizontal distribution of the ECE, the eddy kinetic energy computed in Globe 16. This is longer simulation, and what I'm showing is the mean over the last 5 years of the run. And as I said, you have all the reddish, so the highest value where we have the strong currents. So you can see the Gulf Stream maxima, the Kuroshio currents maxima, also all the tropical bands and a lot of activities, collocated with the ACC. So with Antarctic circumpolar currents. So the difference with eddy kinetic energy computed from the Oscar velocity field is showed into the other plot. Oscar provides its data sets, its satellite-based estimates of the near surface ocean currents with the time resolution of 5 days and the spatial resolution of 1/3 of a degree, so much smaller than what we see into the ocean model here. And actually combine satellites, but also in situ instruments, and taking account of the geostrophic then the components of the velocity, the Ekman and Stommel shear dynamics. The differences are higher where, of course, we have the most energetic area. That's mainly due to the high variability of the dynamics there. So if we look at the western boundary currents, you see mainly it's clearly into the Kuroshio area. So we are in this location now, where actually it's the shift of the currents between the model and the observation that gives this kind of a path into the differences. generally we can say that Oscar is it's higher into the eddy kinetic energy. It's mid latitude, so mainly into the subtropical gyre in the ocean, while Globe 16 performs higher eddy kinetic energy when we move polarward. So, for example, it's very clear into the North Atlantic, where the North Atlantic drift is really well resolved into the model. Here we are still on the energetic. What I'm showing here is the distribution of the mean kinetic energy now, and then the eddy kinetic energy at surface, and then there is the relation between the two into the plot on the bottom right. So what you see here is that all plots are actually in logarithmic scale, so numbers slightly different from what we saw before. Strong kinetic energy are here concentrated into the sharp current, the sharp boundary currents. So if you look, for example, the North Atlantic, the path of the Gulf Stream, then the Labrador currents, even the East Greenland current coming down from the Arctic, it's really evident. Also the Kuroshio here, the boundary currents in the West Australia, and then all the ACC area. They have the largest mean kinetic energy, so that stay confined within the narrow strip along the coast. While the time varying circulation, this actually the eddy kinetic energy component is much more energetic, and you see that actually it's kind of broader, so there is no really evident path following the or such narrow paths following the current. That's mainly due to the fact that we are averaging in time a field days. It's very that varies a lot. So in the end, when you average over time, that looks much smoother into the spatial structure that the time mean circulation. And if you look at the relation between the two, so that's the relation between the eddy kinetic energy and the mean kinetic energy at surface for all the basin, the kinetic energy due to mesoscale processes actually dominates everywhere except into the subtropical gyre interior into the Pacific, South Pacific Ocean or South Atlantic Ocean. So it's generally higher than the large-scale ocean currents in most of the basin, and I will say also in all latitudes. Same things if we move slightly deeper. So those are the same plots, but we are around 2 kilometers deep. The analysis made of the same periods. Actually, the relation between the eddy kinetic energy and the mean kinetic energy into the basin, the global basin, stays the same. So also in this case, the kinetic energy decreases drastically, of course, when we move deeper, but the intensity of the time varying circulation it's always stronger. And if we look at duration, it's much more evident here that the plot is reddish everywhere into the basin, except in location where the boundary current, for example, into the Labrador Sea, gets really deep and can be still identified at this depth. Here is kind of the first example on a specific area into the globe. Well, HEDDIS or resolving HEDDIS into the ocean model is really a key. We are into the North Atlantic. What we're looking at is the SST fields, so sea surface temperature fields, given in Celsius degree. For 1 year, you have daily fields computed by Globe 16. And in this location, actually, it's really evident how eddies actually can form eddies attached from the boundary currents going into the interior of the ocean. That's really evident into the Nordic seas. If you look at the North Atlantic, the inflow of Atlantic water that moves northwards, and then all the heat head fluxes that move from the currents into the interior of the basin. Same things if we look into the Labrador Sea. Here, of course, temperature is slightly different. We are at surface and we look at water that comes down from the Arctic, but actually what you see is pretty similar situation where actually HEDDIS are continuously moving from the ring currents within the open ocean, or what is generally called the convection sites, open ocean convection site in those locations. I choose in particular those two areas because both in the Nordic Seas and the Labrador Seas, resolving eddies means really resolving one of the key processes for the global circulation from the ocean, but also for the climate system. Here, the transformation of the boundary currents means that actually we're losing heat from the current to the atmosphere. We are transforming the properties of the Atlantic water. That means that the water actually gets denser and denser as it travels within the Nordic Sea, so the Labrador Sea, and then will end up to largely contribute to the deep dense branch of the thermal line circulation. So having in a model this kind of a process means that actually the long-term climate signature that we want to have even to the deep ocean, and then the feedback with the atmosphere are well resolved. If we look at the other plot, that's just another example, staying to the Arctic Ocean, on how resolving mesoscale can improve dynamics at high latitudes. What you're looking here is inflow and outflow in and out of the Arctic Ocean. So we have the inflow from the Bering Straits. We are on the other side of the world, so we are looking at the water that comes from the Pacific into the Arctic. And then we have two outflow components through Davis Straits, that means out of the through the Canadian archipelago into the Labrador Sea or into the North Atlantic, and then Fram Straits that is located up to here between Svalbard Island, Svalbard archipelago, and Greenland. So all those are really key key points or key processes for climate model, and they are largely improved both into variability and the mean value when we look this kind of ocean resolution. What I have here into the plot is only an estimate from different data sets of the mean state. I don't have any long-time series in those locations for addressing the variability on this long time series at least. Always stay on the same area. It's one of my favorite area into the global ocean. Another example of how the resolution into the ocean can give benefits to our understanding is actually if we look in details of the composition of the dense overflow that comes out from the Nordic Seas to the North Atlantic. So here you have a schematic with all different currents. In red is the warm water that goes from south to polewards. You have in dark blue the overflow component, so the Danimal Straits overflow water, and then the recently discovered jet, the North Atlantic jet. So while in light blue you have two contributions, there are more surface water and less dense, contributing less to the dense water overflow, and they have the same origins. They just they divide at some point, flowing down along the East Greenland currents. What's actually I want to show here is how having high resolution, we are still at 1/16 of resolution within NEMO, so it's the same configuration. How increasing the resolution actually can help the model to resolve this new jet. So the North Atlantic jet is absolutely absent into eddy permitting global configuration. The dynamic is not there in the even lower resolution where the overflow is really poorly resolved, but start actually to appear and to be well resolved when we increase the resolution and when we can resolve eddies into the Nordic Seas. So sorry, what I'm going to show is actually how the current change when we move north of Iceland, following the continental shelf, that is the location of these new jets, and we will see how this jet can contribute. So I will show you how the model actually reproduces the contribution of this new dense water to the Danimal Straits overflow. What you see here is if we move from section 4 to section 2, we are looking here at always at model outputs. You can easily distinguish that we have core of water that moves from east to west. So red positive value of the velocity field means that the water is going on the left sides of this plot. When you have the blue, so negative value, the water is moving eastwards. So the immigrant current, there is the bluish course that you see here, are moving from the North Atlantic into the Nordic seas, flowing on the western side of the island and then moving over the shelf. But what you see below, it's dense water. If you look at the white line here, you have the isopeak canals of 27.8 and 28 kilogram for cubic meter. There is actually the density of the overflow that we see at Danimark Straits. So what we can see in this plot is that as we move from east to west over the shelf, the Icelandic shelf north of the highland, we can actually recognize a core of dense water. It's pretty cold, that moves eastwards. And then when we stay in section 5, there's actually into the Danimark Straits, where we have all the overflow together. This water is not recognized. So when we stay into the Danimark Straits, we have only one branch of dense water altogether. But the model actually has probably reproduced the jets. And what we see in the end is that if we look at the transport of dense water into the different section, again, what we see that those numbers actually in Sverdrup is the amount of dense water with the typical characteristic as the dense water from the Nordic seas is defined if we move from east to west. So from the beginning of section 4 of our path to the Danimark Straits, the North Atlantic jet contributes to overflow with about 1.5 Sverdrup. There is exactly the same of the contribution that we have from the East Greenland current. There is, let's say, the common, the most typical contribution that has been generally considered as the contribution to the Danimark Straits overflow for decades. So what we can conclude here, that the two jet actually gives half of the Danimark Straits overflow to the North Atlantic. That's also visible into the time series that I'm showing here. It's few decades of runs, and what you see and what you see here is the total overflow in red. So it's the dense water that we are looking at, section 5, and then you have in light blue and dark blue the two different contributions. So in light blue is the one coming down from Greenland, from the East Greenland currents, and blue is the one coming from the jets. And they are really in the same magnitude, so it's always between 1 and 2 Sverdrup in the mean. But also it's nice to actually note that they are not in phase. So when one is actually low, the other one is taking much of the room. So that's actually highlights one of the mechanisms that is behind the formation of the North Atlantic jet. There is the bifurcation of this Greenland current just upstream before going into the Danimark Straits. But that's what actually we can say about the ocean component itself and the effect that the resolution has at high latitudes. But what about climate models? So climate models, anyway, widely used to understand and to predict the evolution of the climate system. And the high resolution also in this case has been identified as essential elements for the development of the system. So to increase the realism of the physical process, to advance our process understanding, and that means to provide more robust answer to most of the pressing question that we have about climate change. But even more critical that in the ocean simulation, the complexity of the complete climate system, all the physical processes and the interaction between them is really crucial in this case, because it costs much more than in case computational speaking respect to the ocean simulation. The results that I'm going to show into the next slides are mainly the results from the simulation runs that all with climate model, with couple model, that have been run and will be performed into the framework on the Horizon 2020 project is called Primavera, and of course CMCC is part of it. So in Primavera, we particularly look at the effect of the resolution on climate processes and variability, with particular interest on the European climate. So the North Atlantic and the Arctic region are one much wider analyzed from the simulation, at least so far. So the overall question is how increasing resolution in all components of the system, but will stick on the ocean components, can improve the representation of the European climate and eventually the prediction of future climates. What you have here is just an easy sketch that gives you an indication. If you look at the first 4 panels in the top part of the slides, you have an indication going, let's say in time, an indication of the evolution of the model resolution in time for the different IPCC reports. So the 4th one was the last one in 2007, and in this case, the ocean and the land resolution, they are represented here anyway, much higher than the first exercise, the beginning of the 90s. But I will show you, if, I mean, you already know actually for the IPCC report, that is anyway not enough, not yet at least. In Primavera, here you have a sketch on how the climate model or the Earth system model can be built. In Primavera, we mainly focus on the atmospheric ocean general circulation model. So when we take in place only the atmospheric components, ocean component, the coupling between land, surface, and sea ice system. What we have here, we will stick on the Arctic and sea ice in this case, and the effect of the ocean resolution in that. But before going on the new high resolution Primavera rounds, what I'm showing is actually how the CMIP5 and the new model from CMIP6 can reproduce the September, that means the minimum sea ice extent into the Arctic. So here you have the plot that shows time series in the top panel from the CMIP5 simulation, so let's say the previous generation of climate models. The time series again show the sea ice extents in September and goes from the 1980 to 2010, so includes the historical and the projection scenarios. And here actually is the most extreme scenarios. So first we can see that the models can reproduce the negative trends in the sea ice extent. So we have a clear decline in sea ice with time, and that follow somehow what observations are showing is the black lines, the thick solid black line that we have into the plot. So the negative trend is there, but we can also note that there is really large spreads among all models. So the uncertainty linked to sea ice is really large, was really large into the CMIP5 exercise. If we move on to other plots, we have results from the new or current generation of climate models. So those are preliminary results from the CMIP6 exercise. We have few models here and 2 data sets. They are the first 2 colors. And also in this case, all models seems to have the negative trends, except some simulation like the green line. There is the low resolution BCC simulation. But anyway, also in this case, the spreads between models is pretty large. We are still looking in September, only September sea ice extent. So seems that the new CMIP exercise has not improved largely the simulation of Arctic sea ice properties. So we do the same exercise and the same analysis on Primavera models. Some of them actually are shared with the CMIP6 simulation, but what we have in Primavera, the added value is the large, let's say, large range of resolution from different components of the system for each models. So what we have here is any colors actually indicates different models. Solid lines are the low resolution, while dashed line represents generally the high resolution, with few exceptions where we have more than 2 resolution. Also CMCC model represented into the plots. So generally what we see is also in this case, the trend seems to be seems to follow somehow the satellite observation. They are always in black. And the key point here is since we want to analyze the effect of resolution, is what happens when we go from the solid line to the dashed line. So if you look like this in WF run, we have really high sea ice area in September when we run the ocean at 1 degree and the atmosphere at 1 degree, so in the low resolution case. But the simulation of sea ice it's highly improved when we look at the dashed blue line, so at high resolution of the same model. But that's not always the case. So we have the same, for example, for AWI. So the resolution gives a decrease into the sea ice extent. But for example, for the high model, this decrease means actually where gets that we having a worse agreements with observation. And there are other models, the one from CMCC is the gray line that you can follow here. That's the solid line, so the low resolution, but this one is the dashed line, so the high resolution. And for example, for CMCC, it is the same for the CNRM models. What we see is actually that's increasing the resolution, we get even more ice. So it's not that clear actually how resolution can impact on sea ice, but generally we can say that increase the resolution into the ocean gives a decrease into the Arctic sea ice, mainly into the September sea ice, so after the melting, the seasonal melting. Here we have the same kind of analysis, but we are looking at the mean seasonal cycle of both the area on top and volume also on the bottom panel. We are still on the only into the Arctic Ocean, so only the northern hemisphere, and we have each month from January to December for different bunch of model, and the mean is computed from 1950 to 2014. So we have more than 10 models here, so it's not that easy to follow different colors. Observation are always in black, but also in this case. So generally, we can say that we can see that the increase in resolution does not necessarily improve the sea ice components. So the comparison between the sea ice modeled by Primavera runs and the observed base estimation, but generally, when increased resolution, we decrease the Arctic sea ice. So if we look at the map of sea ice area in a particular region, and what we chose here is the Barents Sea, because it's one of the gates of the Arctic Ocean, where actually Atlantic water goes into the Arctic, where a lot of changes in terms of the oceanic content and the sea ice are happening, or it's been happening in the last years. So here actually has already been observed a large reduction of sea ice, and what we see here, still comparing low and high resolution of subset of the Primavera models, you have observation in the panel I, and what you see is again that if we increase the ocean and sea ice resolution, so we go from the same model for panel A to D, or for panel B to E, or C to F for the AWI model, we see high level of details into the model. So the complexity of the solution is improved, but not always actually we improve the solution compared with the observation. So again, also in this case, looking at a specific area where the climate variability is really high, the resolution does not correspond systematically to a better representation of sea ice properties. So then we try to understand actually how increasing resolution into the ocean impacts, or why impact the sea ice into the Arctic. So we try to explain the reduction in sea ice with the ocean resolution. So the first hypothesis was that actually the decline into sea ice with ocean resolution is linked to enhancement of the heat transport that goes from lower latitude to the Arctic Ocean through the North Atlantic. And the stronger heat transport is of course due to a strengthening of the ocean currents that we see actually into ocean when we increase the resolution, but also to an increase of the SST. So you have the same model that we saw before, lower and high resolution, and you see that in increasing the resolution, what you're looking at here is the ocean speed, the surface currents in winter, again into the Barents Sea, and you see that there are a lot of smaller scales. Remember that most of the ocean model here anyway only eddy permitting, so it's generally 1/4 degree. But anyway, there are a lot of actually dynamics that emerge, and so all of them brings warm water or more warm water into the Arctic Ocean. If we look on the other side, the other plot here, we have the difference of the winter SST. So we are again in March between the high and low resolution for the four models they are on the other sides. And three of them showed actually there is an increase of the SST when increased resolution. So when the plot shows red, means that the higher resolution is bringing more heat. So the SST is higher into the ocean. When it's blue, means that the lower resolution is actually higher. There is only one exception, is the MPI model, because in this particular case, the ocean resolution is not changing. The resolution is changing only into the atmosphere component. So actually what we learn from this plot is that the increase of the atmospheric, the resolution into the atmospheric model does not impact that largely sea ice, because there is not really big impact on the ocean circulation into the Atlantic, at least not on the SST and the transport of heat polarwards. To summarize what we see, actually what we saw in different areas of the Arctic, actually we clearly find this kind of relationship or high correlation between the heat transport and the decline, the increase of heat transport, the decline of sea ice, but of course only when the Atlantic water that takes the heat northwards is still its surface is still able actually to feed back sea ice. So that's mainly true for the Nordic seas and the Barents Sea area, but we start to lose this high correlation, and actually it's a negative correlation, when we move inside the Arctic, because there the Atlantic water starts to subduct and to disattach from the shelf, from the sea ice interface. So what we see is that into the Barents Sea and the Gene Sea, so the Nordic seas, there is really clear evidence of the negative correlation between heat transport and sea ice area, but that doesn't appear actually in the rest of the basin. And that if you look at the total Arctic, or the correlation within the total Arctic, that's totally based on actually the difference that we see into the Nordic seas and into the Barents Sea. That's the plot that we saw before for only the ocean component at the globe 16. It's similar results here when actually you compute the Atlantic meridional heat transport from the couple model. So generally you have higher transports as actually we saw into the Barents Sea. You have higher transports in all the Atlantic Ocean where you increase the resolution, but also in this case there are some exceptions. So it's strongly depending on also on the feedback on the atmosphere and how resolution actually change in other components of the system. And then going to the conclusion, so I think it's clear to understand the role that mesoscale eddies has into the climate machine, and how relevant it is to explicitly resolve those kind of scale dynamics into the ocean configuration. So we saw that we can better reproduce the polar wave transport, the energetics of the ocean, and we can also represent some peculiar processes that can have large impact on the climate, but they are totally absent at lower resolution. When we move to the climate model, the situation gets a bit more confused. So the impact of resolution is evident into the ocean and into sea ice, but it's difficult so far, at least for the Primavera simulation that are now available, to actually identify one single trend for all models. So for sure, when we think about the climate machine, from the modeling point of view, we need to fully understand the role of the complexity of the model and the resolution. We need to spend more time and more energy in doing that. I think I can conclude with that.
Thank you very much, Dorotea, for this really exhaustive talk. We don't have a lot of time, but maybe we can answer a few questions. If I can start, my first question is, so you know that at CMCC we are involved in CMIP efforts since more than 10 years ago, and we always push it on the resolution side, both for the ocean and the atmosphere. And this is something that we still continue to do, and you are describing here the importance of the horizontal resolution of the ocean side. And well, my question is, once the mesoscale has been reached, do you think that it is time to spend CPU computational power, because we know that this is really CPU time consuming, this kind of effort? So my question is it time to spend CPU time for the development and improvement and tuning of our models? I mean, testing, parameterization, sensitivity experiments, and so on, or is it still time to push on the resolution side?
So the question is if you want to push only on the resolution or also on the complexity of the system, right?
Yes.
So, I mean, first I will look at the resolution as part of the complexity of the system, because increasing resolution also means that somehow you have to adapt the physics that your model is resolving to the grid spacing. So you cannot use the same kind of parameterization at 1 degree, it's 1/12 of degrees. So two things go somehow in the same direction. And being a modeler, I would say that, of course, resolution takes priority if you think about the possibility that we have now, in the sense that the model are, at least for the ocean point of view, kind of ready to run and to resolve this kind of dynamics. The only limitation is probably only the computational costs. But of course, again, being a modeler, I will totally support, and also be involved into the name of evolution. I totally support the other sides of the medal. That's improving the physics into our code is the key points, the major point that we have to work on.
Okay, thank you. Just another quick question: how do you validate your model at the global scale? I mean, since you are reaching such a high resolution, where do you get the observational data set to validate it?
That's kind of a question that I get anytime that I present the Globe 16. And the answer is I don't have data sets at high resolution, in the sense that you try to do the best with the tools that you have available. So for example, even if you want to use satellite data, they are not at this resolution. But for example, you have to get the best of what is on the table. But a new branch actually of satellite missions will bring us a lot of new products improved from the instrumental point of view, but also from the resolution in the next years. So that's new. It's a new branch of science that's for the validation of the model will bring a lot of new things. One slide, probably it's behind here. Then no, I don't know if I'm still sharing the screen, but in this case I can show if it's there. It's there. That's the same plot that I showed before, for example. So it's the comparison of what for the eddy kinetic energy with the Oscar, and then you have another estimate by satellite. It's newer. It's called globe currents. It's higher resolution, but actually it's based on the same kinds of instruments. Of course, data are treated with different algorithms. But if you look at the two plots here, they are both different with the globe 16, and you see actually the path it's different. Globe current is much more energetic than Oscar and then our model. Which one of the two has to be used, I have no idea, and also have no indication on the certainties into the two data sets. So you use both of them and you try to understand for the differences between the two and your model, how actually you can improve the numerical tools that you have.
Okay, thank you very much, Dorotea. Thank you again. We have to stop here. And thank you all, and see you at the next CMCC webinar.